All right, so fission reactions. A fission reaction, simply stated, is a reaction in which a heavy nucleus, one from an isotope usually that has more than 80 or so protons, ends up decaying into smaller isotopes of smaller atomic numbers and smaller atomic masses. Sometimes the fission reaction needs to be kind of pushed forward by adding neutrons to it, as I'm depicting here in this reaction. But you're going to have some direct products, and usually in some of these fission reactions, specifically the ones that get used in um, nuclear plants, to power up an entire city, um, what you end up doing is selecting isotopes that, yes, you bombard initially with some neutrons to undergo the fission event, but that fission event itself produces more neutrons. So this is kind of like a self-sustaining chain reaction that keeps on going, producing energy until you run out of, the fuel, or until you go down a certain level. All right, so let's say that the atomic mass of one of the products is Z1. What that means is that atomic mass of the second isotope in this case will have to be Z minus Z1 to give you the same atomic number on both sides. For the atomic masses, if the atomic mass of the first isotope is A sub 1, then the atomic mass of the second isotope will have to be A sub 1 plus 1 minus, A minus 1 plus minus A sub 1 minus 1 times A, right? So we see all of that here. So we're basically adding what we have on the left side of the equation, we're adding what we have on the right side of the equation, and we're subtracting it from the masses of the reactants to get the mass of the second isotope. Now, the way I have it right here, it looks very funky and ugly, but as you'll see in a second, it's not even remotely as bad as it looks right now. So I'm going to give you an example. For this type of problems, by the way, I can't really have you predict what the products are going to be because there are multiple isotopes that get formed. So I'm going to have to give you everything except for the one species that you are, finding out. So case in point, I could give you something that looks like this. I could tell you that uranium-235 reacts with one neutron to produce 3 other neutrons, cesium-143, and some other species. And what we're going to do is determine what the other species is, right? So what we do is we add the numbers on the bottom first. So we have 92 plus 0, which is 92. Over here we have 55 plus 0 times 3. 0 times 3 is just 0, so we have 55 plus 0. And so 92 minus 55 is going to yield 37, right? And that's the atomic number of the missing particle here. Now we do the same thing with atomic masses. We have 235 plus 1, which is 236. Over here we have 143, and we have 1 for the neutron, but there's 3 neutrons, so we actually need to multiply the 1 by 3 and add it to 143. So in reality, we have 143 plus 3, which is 146. And 146 needs to be subtracted from 236, ultimately yielding a value of 90. So if we look at the periodic table, element 37 is actually rubidium. So we just input the symbol rubidium for the missing particle. And as you can see, the logic is just the same as before. You add the top numbers together, they have to equal the same on both sides. You add the bottom numbers together, and they have to equal the same on both sides. All right, now fusion is in some ways the opposite of fission. Instead of starting with a big isotope and yielding smaller ones, what you do is you take 2 smaller ones and make up a bigger one, right? So you fuse the small ones together and you get a bigger isotope altogether. And an example of this is basically 2 hydrogen atoms or 2 hydrogen nuclei reacting together. In this case, you could produce deuterium, which is the heavier isotope of hydrogen, but we got to make sure that everything matches up, right? So the numbers on the bottom, we have 1 plus 1, which is 2. We only have a 1 on the bottom for the product, so that means that we're missing another 1. Looking at the masses, we have 1 plus 1, which is 2 on the reactant side, and we already have a 2 for this hydrogen isotope. So that means that the mass number for X has to be a 0. And the only particle that matches up this description of having no mass but having a charge of +1 is the positron. So this will tell you that this process of fusing two protons together yields deuterium, a positron, and your neutrino. So that's pretty much the idea, right? You have lighter nuclei, bring them together. You still have to have the same number on top on both sides as you do on the bottom as well for both sides of the equation. All right, so that's basically the idea with fission and fusion. So let's talk about the kinetics of nuclear reactions, because this is the part that links up nuclear chemistry to kinetics. And this is the reason why I decided to discuss nuclear chemistry this early on in the course. All right, so as you may recall, we talked about the different orders of reactions. We talked about zero order reactions, first order reactions, and second order reactions. For nuclear reactions, since technically speaking, you don't have multiple atoms reacting together, it's simply just the nucleus, which is way inside the atom, undergoing decay. The reaction depends just on the concentration of that one nucleus. And so by default, the nuclear reactions that we deal with are first order reactions. So the equations we're going to be using for them are technically the integrated rate laws, right? ln of A over A naught equals negative K times T. And that also means that we're going to be dealing with the half-life equations, which for first order reactions equals 0.693 divided by K. Right? So that's the half-life equation for first order reactions. So these are the two equations we're going to use in the context of nuclear reactions. So let me give you an example. Oh, and by the way, we need not be restricted to concentrations for using the integrated rate law. So A doesn't need to be concentration. It could, but it can take up most any form. It could be the mass of the radioactive isotope. It could be the activity of the radioactive isotope. And I'm going to give you an example of that right now. So we have technetium-99 decaying by beta emission. The half-life is 6.01 hours. We know that the sample has an initial activity of 300 disintegrations per minute, or DPM. And basically what we want to know is, if we keep this isotope for 7 hours, what's the final radioactivity or the final activity of this isotope? So we have a few things here. We have the activity, the initial activity. We have the half-life. We have the final time. So we can use the half-life to figure out the rate constant. All we have to do is simply cross-multiply the half-life and the rate constant together, so that we can find out the rate constant, right? So we multiply, we divide 0.693 by the 6.01 hours, which is the half-life of technetium-99, and this will give us a value of K of 0.115 per hour. All right, now that we have the value of K, we go to the integrated rate law for the first order reaction, and we input what we know. The initial concentration, or in this case the initial activity, is 300 dpm. So you can input 300 for A naught. The value of K we just determined to be 0.115 per hour, and the value of T, which is the time, is the 7 hours presented here. So technically speaking, we have everything except for the final activity of technetium-99. So we multiply negative K by the time. Then we take the anti-log of ln, which is e to the negative 0.805 in this case, and we multiply that by 300. And when we do that, we will find out that the final activity is 134 dpms. And so what you can see is that the process is no different at all than what we did in the kinetics chapter. It's pretty much the same thing. You just have to remember that this is a first order reaction exclusively. All right, so I'm going to finish this video by giving you my final thoughts on nuclear chemistry, because after all, this is a really cool topic. We don't spend a lot of time on it, but the implications of nuclear chemistry are just huge, humongous. I told you that during the Manhattan Project, the atomic bomb was developed, right? And the ideas of relativity led up to the development of the atomic bomb, which, depending how you want to look at it, It has perhaps some good connotations. It has a lot of bad connotations with it. Uh, and to this day, the word nuclear, people identify that with bad things, even though something with a nucleus doesn't necessarily need to mean that something bad's happening. In fact, MRI, it's called magnetic resonance imaging, and they call it that because what actually happens there is a process with the nucleus. But if they were to call it, the proper thing, nuclear magnetic resonance, people will freak out because of the connotations to the atomic bomb. Now, as destructive a force as it is, right, having atomic bombs, going off on Earth, this is ironically the very same thing that keeps us alive, right? So this is technically a hydrogen bomb that I'm depicting. And the reason I'm saying that this is what keeps us alive is because the sun literally does this. The sun is a big ball of hydrogen bombs going off every second of every day, every single time. And the energy that's being produced is simply the energy of taking two hydrogen atoms and fusing them together to make initially deuterium. The deuterium is fused with further hydrogen to make helium-3. And tritium that gets formed in the process reacts further to give you helium-4. That's basically what our sun is doing. And in the process of undergoing these fusion reactions, which is the same thing as saying exploding these hydrogen bombs, it produces all the energy that we require to survive on Earth. So as bad a thing it is, it's actually the one thing that also keeps us alive. And the beauty of this thing is that by looking at relativity, there's a link, a tremendous link that puts basically the theory of the very large, the galaxies, the stars, with the theory of the very small, the atoms, right? And pretty much the solar evolution of stars. You start with a planetary nebula that creates your star, you create your planets. The star consumes its energy, thus producing energy in the form of fusion nuclear reactions. And once that fuel is consumed fully, that's when the star starts undergoing its cycle of turning into a red giant. Um, and once that consumes all the extra fuel that it possesses, it turns into another star. And this kind of undergoes a process that ultimately, at least for our star, we're going to turn into a white dwarf at the end cycle of our sun. But other stars that have a lot more mass, they can go through other events that not only yield, a supergiant star, but ultimately could produce a supernova that turns into a neutron star or even a black hole. But it's in this supernova event that all of the heavy elements, platinum, gold, um, mercury, all the precious transition metals are basically produced during these supernova explosions. And during the course life of the stars, you are actually producing elements by undergoing fusion, pretty much. And in the supernova, not only do you get to produce the higher massive elements, but in the supernova, you have a huge explosion that basically spews out all of the elements into the outer galaxy. And some of those elements, of course, have reached the Milky Way. They have reached our solar system, and those elements have turned into, the planet that we live in, Earth. So it's not all that far-fetched to say that all of us are actually uh, made out of stardust, because after all the elements that we have that make us up came from a star. So it's actually kind of a beautiful grandiose way of looking at life, right? And ultimately, it's explained by nuclear reactions. So that's the beauty of this chapter. That's the beauty of this topic. And I highly recommend that you look deeper into it. If you are interested in this topic, definitely look into um, nuclear physics, elementary particle physics. That's when these things get really interesting. But that's all I have to tell you in regards to nuclear chemistry. I hope you enjoy this lecture. I certainly enjoy talking about it, and it has a special place in my heart. So, with that all being said, I will see you on the next lecture series. Okay, bye bye.